Welcome everyone. So today, as I said, we are going to cover equations. We're going to be looking at types of reactions. Okay, so I'm going to be going through some of the theory a little bit faster, just because we can easily just quickly read it. Please feel free to ask questions along the way. So I'm going to go on based on the questions. So if no one's stopping me along the way, I'm just going to keep going. Okay, so please, if at any time something's a little confusing, you want kind of clarification on something, don't be shy to ask. Okay, so balancing equations. So balancing equations follows the following law, the law of conservation of mass. Okay, so what it states here is that matter can be changed from one form into another. Mixtures can be separated, all that stuff. So what it really means is that if you add up the mass of all the reactants, okay, so in a chemical reaction, you're going to have, let's change the color here. Okay, so we're going to have an equation. And so we're going to have, in an equation, we're going to have our arrow. We're going to have stuff on this side of the arrow and stuff on this side. As we're going to see in a moment, these are, everything on this side of the arrow are known as the reactants. You can have either one reactant, two or more reactants. On the other side, you're going to have your products. And you're going to have one product, two products, three, many, whatever. It all depends on the type of reaction that we're going to be looking at. We're not going to worry about the types just yet. All we want to look at is about balancing. And in order to balance, we need to understand this law. And what this law states is that if I start off, let's say, with 100 grams of reactants. So we put together, I don't know, let's say product A, or sorry, reactant A with a reactant B. When they react and they form a final product, or maybe a combination of products, if we started off with 100 grams of this, we need to finish also with 100 grams. Okay, that's the law of conservation of mass. That the mass, so the idea that matter is neither created, so we can't create matter, and we can't destroy it. We just shift it around to form new products, with which entail new chemical compounds that form. Okay, so so when we're mixing things together, understand that the elements, the atoms of each compound that we're mixing, reshuffle themselves to form entirely new products, but the entire mass of our final product must still be there. One of the questions I give in the assignments, I don't know if I gave it in your assignment this year, but one of the assignments that I gave, I ask that we burn something in 100 grams, or I think it was like 1,000 grams of something, and in the end we only came up with 30 grams of a product. Okay, so the idea that we start off, let's say, with 1,000 grams, but we ended with only 30 grams, how can this be? This doesn't follow the law of conservation of mass, but technically it does, because the product that we weighed was weighable. Okay, so what that means is the end result was probably some kind of a product that was either solid or a liquid that we can technically physically carry and put onto a scale, which means the remaining 970 grams that is unaccounted for from the original 1,000 grams must have been lost somewhere. Okay, but how was it lost? Well, in the example of that assignment, that question that I gave, this most likely was in the form of some kind of gas, whether it be carbon dioxide, because it was a burning reaction. It could have been any other kind of gas, but typically gases, like think about the gases all around our room, right? So there's oxygen gas, there's nitrogen gas, there's carbon dioxide gas, there's water vapor. That's all in the room, but we can't kind of collect it and put it onto a scale and actually weigh it out. So what was weighable in the end of this reaction was just the 30 grams of some kind of solid or liquid. The remaining 970 grams must have gone somewhere. And that most likely was in the form of a gas that we don't really see, right? If something gives off a gas, right? We we put a solid, we mix a solid with a liquid, and all of a sudden bubbles start to form, and the bubbles rise to the surface of the beaker, and then those bubbles pop when they get to the beaker. Think about a pop can or a pop when you pour into a glass and you see the bubbles, and the minute they reach to the surface they pop and they release carbon dioxide gas. And so that gas gets lost, but it doesn't mean that it's been destroyed. It just means that it kind of just left the so-called system. It was there in the original can of pop. It was originally there in the bottle of pop, but now that we've opened up the system, we've opened up that sealed container, we now allow for us to lose some of that mass in the form of a gas. Okay, so let's clear all this and move on. Okay, so when we're balancing, what's really important, first off, is to be able to count the number of atoms that we have. So if I write a formula just like I have there, Ca, it implies that I have one atom of calcium. Okay, let's look at the next one here. We've got a subscript. So the subscript 2 in this example, N2, nitrogen gas, that 2 implies that we have 2 atoms of nitrogen. Okay, so if we look at a formula like H2O, for example, right, H2O, this 2 implies that I have 2 H's. The single O here implies that I have 1 oxygen. Okay. So subscripts outside of the brackets. Okay, so here's where things get a little bit tricky, but again, if you understand the rules of math, this 2 would get distributed within the brackets and within the brackets only. So in this case, we're going to have 3 barium atoms, right? That subscript here, 3 barium. Originally, inside the brackets, we have PO4. So that PO4, right, implies, well, we have 1p, but it gets multiplied by that 2 for outside of the bracket. So we have 2 phosphorus atoms and 4 oxygen atoms, but now that 2 gets multiplied with the 4 to give us a total of 8 oxygen atoms. Okay, now another way to look at this, and this part is important, is to be able to, if you can identify, let me change the color here so we can see what I'm doing. If you can identify what's in these brackets here is a phosphate. Okay, it's a phosphate polyatomic ion, what we looked at in 4.3. So go back to 4.3 to find out the polyatomics. So what we have here is we can look at it in 2 ways. We can separate the P's and the O's and count it as we have here, right? 2 P's, right? 2 phosphorus and 8 oxygen. Or we can look at this as containing 2 phosphate ions. This way is going to be a lot helpful when it comes to balancing, because when we're balancing, we're going to want to be able to collect these polyatomics, because it makes balancing so much simpler, and you'll see that when we actually get to some of the sample problems at the end of this chapter. Okay. Okay, so when we have a subscript, or sorry, a coefficient in front of something, whether it be the atom or a compound, that three would get multiplied within. Okay, so in this example, 3 carbons. These big coefficients, typically we put those coefficients in when we balance these equations. That's the only time those numbers ever really technically appear. Okay, so this so-called coefficient that we're gonna see here, this coefficient is only seen when we are balancing equations. So typically, they're not found commonly in formulas. Okay. Okay, so here is where we would see the coefficient in front of an actual compound. Okay, so if we look at this compound here, this 3 would get multiplied in with the Fe, this 3 would get multiplied with this S, and this 3 would get multiplied with the O4, which would give us a total of 3 irons, right? Because there's 1 here. So let's ignore the 3 for a moment. So there's 1 Fe, 1 iron, so 1 sulfur, and 4 oxygen. But now that the 3 is there, okay, now that the 3 is there, that 3 gets multiplied with everything only in that compound. Okay, so only in that compound to give us that total of 3 sulfur. Oops, 3 sulfur. So we've got 3 iron, 3 sulfur, and 12 oxygen atoms. Now, if we identify here, for those of you who know their polyatomics, will understand that SO4 is the sulfate polyatomic ion, which means that I have 3 sulfate ions. So instead of separating them as 3 S's, 12 O's, I can separate it as 3 SO4 polyatomic ions. And like I said, this part here, you're gonna see what I mean by it when we get to the actual balancing of equations. Okay. So here we have some sample problems. Try these out on your own to help you count them. The answers are just will follow this slide. Okay, so we're going to move on from this slide, but let me just kind of help you kind of go along the lines of how to kind of count some of these. So we're going to do 2 of these, or just parts of 2 of these really quickly. So the ones that I want to kind of cover is this one and this one. There's a reason why B I want to do, and the reason for B is we've got hydrogens written out twice in 2 different spots. Why didn't they collect the 2? And so if you know your polyatomics, you will know that this part here is the ammonium ion, ion, okay, and this is the acetate ion. Okay, so really what we had, this is an ionic compound. So that's the reason why, like the acetate polyatomic ion and the ammonium polyatomic, they both contain their own hydrogens. So that's the reason why they're separated. But when you're counting them in total, like I said, you can either count them as ammonium and as acetate as separate entities, or if you're gonna count them, we've got 4 hydrogens here plus 3 hydrogens there to give us a total of 7 hydrogens in this one whole formula. Sorry for all the red that's written, that just kind of covered around that formula. Okay, and with regards to letter F, because of the brackets and the coefficient in front, so this 2, so this little 2 here would get multiplied in the brackets. This 2, however, and let me use a different color, this 2 here would get multiplied within the brackets, but it would also get multiplied with the rest because they're all connected in one. They're all connected as one full formula. Okay, so that's a full compound. And so what we have here is, in fact, we've got two polyatomics. The polyatomics that we have here, again, the ammonium polyatomic is right there. And this one is actually, if you look at chapter 4.3 in my list of polyatomics that I've labeled as, so in my slides, I label them as polyatomics intended to be memorized. But because we're going to be doing this stuff online, it's going to be hard for me to kind of make sure that you're not using a formula sheet to get to these polyatomics. So with regards to any future test or quiz, or even I don't know what we're going to do for the exam. I'm still getting word of what how we're going to be running this course. Is for tests and quizzes, you'll have the sheets. So technically they'll be kind of open book, but they will be timed. So you're going to have to kind of keep in mind the time, but don't worry about that. Like I said, we're going to see what we're going to try to do. The last thing I want to do is kind of make this course any more stressful with the, considering the circumstances that we're in right now. With everything. So right now we're just kind of trying to, take things easy, get as much as we can in preparation, where I will be covering the entire course, but at the same time, I'm going to try to do what I can to not make it as stressful on you with the number of evaluations that I typically would have done throughout the year when we're in class. Okay. Anyway, so this is the dichromate polyatomic. It's on that list. The slide is entailed polyatomics to memorize, but you won't need to memorize. But those are the polyatomics that are important. Okay, so please go back to that old Zoom lesson where I talk about which polyatomics to know. Okay, oops, let's clear that. Oops. Okay, so there are the answers, but we're going to move on to the actual, to the balancing. Okay, so chemical equations represent what happens to atoms and molecules on a molecular level. Okay, so we can't really see each individual atom if we were to look at a beaker of stuff reacting, right? We got to look at what each compound is in an actual chemical reaction, and then see what they form. Okay, so we'll see that in terms of formulas that we put together. Okay, so how are equations written out? Well, some of the wording that you're going to see are as follows. Sometimes it'll be as simple as seeing the arrow already written. So here's a great example here. Up at the top, sodium plus chlorine produces, okay, sodium plus chlorine produces sodium chloride. Okay, so here I've given you pretty much the order, but understand that sometimes I might give you it in words, like as a sentence, as we see here at the bottom. So if you look at the bottom here, sodium reacts with chlorine. So sodium reacts with, that's the plus, chlorine to form, that's the arrow, sodium chloride. There's the product. Okay, other words, instead of to form, I might use yields, makes. Sometimes I might word it as sodium chloride is formed. So think about the way I'm wording it. So sodium chloride is formed when I mix sodium plus chlorine together. Notice how I said the product first, and then I said the reactants. So not always are you going to be given in the exact order the way it's written. I might go backwards and say, this is what we're making when I mix sodium and chlorine together. Okay, so be careful of the wording. Okay, so let's move on. Okay, so as I mentioned before, um, all the reactants are what are found here in front of the arrow, and the products are what are made. One thing to make note of, it's telling me I'm running out of time. So I'm gonna go for the next. It's telling me it's giving me a 10-minute countdown. Okay, so after when the 10 minutes over, we're going to reconvene again. Okay, so anyhow, as I mentioned before, the reactants, we start a reaction, they form products. Now, okay, when we write chemical equations, it always has to be in this order, okay? So you must always have your arrow going in the same direction as the English language is read, from left to right, okay? So we will never write the equation or the arrow in the opposite direction, okay? It always, okay, so this is wrong, okay? We always, always, always go in that direction. Be careful also, it is never an equal sign. Okay, it's never an equal sign. It's always an arrow that separates it. So it's not reactants equal products. That's wrong. Okay, it's reactants form products. So if we put an equal sign, we're saying that they're both the same. They're not the same. So if you look at that example that we did, sodium, right, reacts with chlorine. Chlorine, by the way, is a diatomic. We can never just keep it as chlorine. Chlorine is diatomic, so we always put a little 2. Forms sodium chloride, NaCl. Why is it NaCl and not NaCl2? Because of this 2. This 2 only implies for the fact that it's diatomic. There's 7 diatomics. Um, and I think we'll see them in a moment. If not, go back to I think 4.1. I have the list of the diatomics. Anyhow, how did we get this formula, and why didn't that 2 appear? Well, going back to the nomenclature and writing the formulas, Na, right? So sodium chloride is a metal nonmetal, right? If you look at the oxidation number, the ion, right? +1, -1. The ones cross over, remove the charges, simplify, remove the ones, and the formula works out to NaCl. And that's where we get that's where we get that formula. So remember that the stuff from chapter 4 is ongoing into this. And in fact, chapter 4 and 5 are vital as we move forward into unit 2, which I think we will be going into unit 2 next week. Okay, so let's clear that. Okay, so there we have the equation here at the bottom. Okay, so we've got the Na, we've got the Cl2, and it forms the NaCl. Now, these little subscripts, these are not vital yet. We are going to see these in Unit 3. But for now, don't worry about them. If you see them, you see them. All they mean, all they do is they state really the state. They represent the state of the formula. Okay, so the S's imply solids. We could use an L if they are liquids. We'll use a G if they are gases. And then we might use the letters AQ, which means that they are aqueous. And what anything that's aqueous, so if you see a formula, so here if you might see something like this, BaCl2, and you see the letters AQ, it means that this BaCl2 has been dissolved in water. That's what AQ stands for. Okay. So let's, one more thing to make note. This equation here at the bottom is actually not yet balanced. Okay, that's not yet balanced. And how do we know that it's not yet balanced? Well, there are no numbers here in front. Well, yeah, I lied. There are numbers. It's technically a 1 that's in front of all of these, but there have been no numbers changed on our part. Okay, so technically, because there are only ones in front, this is what is referred to as a skeleton equation. So sometimes when I give you the words, okay, when I give you the words of a formula, okay, as I did here, sodium plus chlorine produces sodium chloride. One of the first steps you're going to want to do is actually put together this skeleton equation. And this is what you're going to be putting together before you actually balance. Okay. So, like I said, the little states, the little S's, the G's, the L's, we're not going to care about them for now. Oops. Where is it? Okay. So, moving on. Okay, balancing equations must always obey the conservation of mass. In other words, matter is neither created nor destroyed. So if we look at this reaction here, notice how what we start with sodium and chlorine. Look at what we have on the product side, sodium and chlorine. Okay, so notice that none of the atoms have disappeared. Okay, none of the atoms have disappeared. Okay. So here is an example of a balanced equation. So the top one here, we have our skeleton equation before we balance it. The bottom one here is where we've actually put the numbers to balance this equation. Okay, and what do we have here? So here are the steps. So what we're going to do is I'm going to quickly rush through these steps. I've got 3 minutes left in this session. I'm going to log out and I'm going to log back in. So just come back and join us again and do the sample problems in the second half of this lesson. Okay, so here in the steps, what you want to do is you're going to list the elements and you're going to separate your reactants and product side. Okay, and you'll see this when we actually go through some of the sample problems. So you're going to start to balance both sides by putting numbers in front of each of the molecules. So you cannot change any of the little numbers in a formula. The only place you can put a number to balance is in front. So it's the big number, the big coefficient that's in front of any of the compounds. One of the things to always want to balance, if you have them, is to try to balance polyatomics first, leave any diatomics last. Okay, so you want to, when you're balancing, you want to make sure that all the atoms on your reactants equal the same number of reactants, the same number of atoms on the product side. And then finally, you might want to rewrite the equation so it's a lot cleaner or whatnot. But you'll see what I mean when we actually go through the sample problems in the second half of this lesson. So I'm going to stop this lesson right now. I'm going to log us out, or I'm going to get out and then restart this lesson. And I'm going to also take some questions. So I'm just going to let the video, because it's going to be buffering a video. It's going to be compressing the video. And so in that time, work on the sample problems at the beginning of this this session when we're asking you to count the atoms. Okay, so see you all in a moment. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.